All right, this is a continuation of another video where I'm working to solve this problem right here. I'm trying to find P of t for this differential equation, which is the logistic growth model with P of 0 equal to 100. Right now I'm at this spot. So if I were to take this equation right here and write it as 10x equals 33 minus 11x, that's kind of where we're at right now. What would you do? You would move the 11 over. So this guy right here is this p, and it needs to be moved over. So if I do that, I get 4p times e to the negative 1/2 t plus p, that's this one moved over, equals 500. And now notice I can factor my p out. The way I like to usually do that is to write the variable here and then put a set of parentheses and then say to myself, what do I need in here to make this line equivalent to that line? Well, I definitely need the 4, and then I need the e to the negative 1/2 t, and then I need a plus 1 because that will give me this equals 500. And we are almost done. This gives me P of t equals, I'm going to divide by these parentheses. I won't write them twice, but you should see that. What's it give me? P of t is 500 over 4 e to the negative 1/2 t plus 1. And that's the solution. And I'll talk about it graphically in a moment, and it'll make a lot of sense. So the issue with this problem is that depending on which of the steps you take in terms of what I've highlighted up here and what suggestions I've made to make it easy, your answer may be different but still correct. The most common answer that is also correct would be P of t equal to 500 e to the 1/2 t over 4 plus e to the 1/2 t. Notice I could get to this line by multiplying by e to the 1/2 t over e to the 1/2 t. If you could see that algebra, they're equivalent. The spot where this, where the decision point up above that would have gotten you to this answer as opposed to this answer is right, where did I do it? Oh, right here, this step right here with this multiplying by e to the negative half or dividing by e to the half. So if you hadn't have done this line or this line, then you would wind up like that. Both answers are totally fine. I like this one better because you can see what happens as t goes to infinity. The limit as t goes to infinity of 500 over 4e to the negative 1/2 t plus 1. Well, that term, the entire 4, this whole piece right here, goes to 0. That goes to 0 as t goes to infinity. So it gives me 500 over 1, which is just 500. And I like that that is easier to see in this equation than it is to see in this one. It's not that big of an argument to make it for this one, but I just like it better in this one. And that 500 is significant because it matches this graph. Remember we said we had a limiting population or a carrying capacity of 500. So this curve that I drew here, boom, that goes up like that, this is the sketch of what the curve that we just found should look like. So we're going to go over to Desmos real quick, and I've got this graphed in there. Okay, so you can see here that actually, okay, now you can see what I've got plugged in here. So this curve is the one that we were just talking about. It's 500 over 4 e to the negative 1/2 t plus 1. Notice it gives me that exponential, or that climb. Here's that steepest spot right here at 250. It's a point of inflection there. And then it turns to concave down, and begins to taper off, and it gets closer and closer and closer to this dotted line of 500, the carrying capacity, until we can't really tell visually that it's different. But if we zoom in, you'd be able to tell. So what I've done here is I've put a bunch of other curves that would have had different C values. Remember our C, I think, was 1/4. So watch, if I put these blue ones up here, those three, this would be a starting value of 250. This would be a starting value of maybe 40. I have no idea what starting value that is, right? But we've got all these different starting values. So when I talk about solution curves on the graph that we were just talking about before, they are all different curves with different C values, and you can see that they all have the same shape. In fact, to me, it looks like if I could grab this thing and slide it over to the right, it would land right on top of that graph. And that's actually the case. If I slide them over, they will land on top of each other. I also have a handful here in green of curves that would be representative of starting above the carrying capacity. So those I would have solved for the C's with, like this one, for example. I solved for that C with an initial value of 600. So if we start at 600, it comes down like this. And then if I zoom out a little bit and over, look at this one. This one starts all the way up at 1,000. What happens is it goes down really quickly and then levels out at the carrying capacity. And notice all of these equations flatten out and land on that 500. So hopefully you see that the red graph lines up with what we said it should be in terms of like starting at 100, going up to the carrying capacity, right? And then I also really want you to understand what all these lines are that are drawn and what they're representative of, like what the lines in my other, I want you to see that these lines here are the same as these lines here. And in fact, maybe these should even be tucked closer to this side, but they still get the general gist of it, right? So hopefully this makes some sense and you understand logistic growth models. They're long problems, but they put together a lot of the calculus that we've learned. They put a lot of algebra into it, some tricks, some cover up, stuff like that. And then they're also super, super applicable to population models and to all kinds of other places in science and reality.